Come on, come here, boy. Come on. You freaky dog. I don't need to analyze every word that comes out is a lie. Make you look like it's
Hey there. G'day all cutters.
finish line. If you gotta know the truth was gonna let you go. You was fine, never mind. Unpredictable. Fade eye off the ground, you ain't no one.
Well, it's another Sunday Toolbox Tech Talk. Got some fun stuff lined up for you.
You wish really was about your life. Basic bullets, with my bullets. Does your wifey know you're begging for my notice? Promise you're the same. Running for the meds.
All right, I'm just getting more crazy with the season. How do you like the virtual bling in the background there? A little bit of laser action. Yeah, you got to have that. Well, it is the season for all things silly. So whatever you're celebrating at the moment, whether it be Christmas, forthcoming Hanukkah, Yuletide, Bodhi Day, Quasar, which is another one I haven't heard about, but there you go. There's a whole lot of reasons for people to get together and celebrate. But for today, we're going to be talking tech again. So, yeah, nothing quite silly, something very practical, which is all about understanding how to rate isolation for DC devices on a PV array. Now, already I've had a few people pipe in a few emails to me saying, are you going to cover circuit breakers as well? Well, it's all about isolation. It doesn't matter whether it's a switch or a circuit breaker. It's still under NZS 5033 needs to meet the same requirements. So that's kind of where we're going with this one. Just checking in the chat there. G'day, guys. Hi, Ray. Thanks for promoting my channel there. That's great. Hi, Dave from Dungog. Lovely Dungog. Yeah, it's been a while since I've been up that way. Yeah, and Ray's celebrating time off work. I guess quite a few of you might be doing that right now. So what better way to spend a Sunday than watching some silly guy in Bling talk about safety standards? Yeah. Okay, let me just fade the music out. So there we go. First up, a little bit of news. So, I'd like to kind of cover what's happening in our world of all things renewable and electrical. And one thing that just popped up into my feed, which of course I was watching the news about this, is this amazing offer for electric vehicles that's come up. So, what do we got here? So, thanks to Chris Bowen for announcing a $150 million incentive for low to middle income people to buy EVs. Now, as a relatively new EV owner, I've only had one for a couple of years, I'm just over the moon. That the incredible cost reduction of having no fuel. I mean, I live on a mountain and I drive typically 40, 60 kilometres a day up and down this mountain, delivering kids to schools and sporting events. It was costing me a fortune every week. And also it made me feel guilty about traversing the mountain in my old diesel troop carrier. So now I have guilt-free travel, kind of. I guess the only costs are I had to replace a couple of tyres, punctures actually, bad ones. Apart from that, nothing. Yeah, it's great. And it charges from solar here, of course. At the Smart Energy Lab, we've got about 8 EVSEs, so it's electric vehicle charging stations, like your conventional ones you'd have at home. And we've got a couple of fast chargers as well, a 50 and a 25 kilowatt DC charger. And one of them is bidirectional. Yes, bidirectional. It's a thing. So, yeah, that's a bit exciting for those who are thinking about buying an EV. The government's stepping up there and giving you a leg up. So, yeah, cool. As usual, I'd just like to remind people if they want to ask questions, put them in the chat. If I can answer them live, I will. If I can't, I'll get back to you. Maybe it'll be another video, because actually a lot of my video ideas come from your questions, whether it's live or via email. So feel free to do that. And I'll just throw my email address in there, because I know it's dangerous to give away your email, but there you go. There's always things called a delete button if it gets really bad. So feel free to email me with questions that you might have thought of after this live stream. So let's jump into it. Now let me just get my little setup going here. Make sure I've got my focus correct. And push my keyboards around a bit. There we go. Okay, so back to drawing. I love drawing stuff and explaining things. So let me start explaining the problem. The problem being with DC isolators or any device that's used for isolation is that, for a start, we don't have a standard PV array voltage. We have whatever it is. You actually manufacture the voltage by configuring the number of modules in an array, and you'll come up with a particular open circuit voltage. Now remember, open circuit voltages, so this voltage here is the open circuit voltage of the PV array, and that also has to be temperature compensated. So the colder it is, below 25 degrees Celsius, the higher this voltage goes. So I'm just picking 600 as a nice round number, but depends on what your array is. And just speaking of Ray's just asked, does the EV have more battery storage than your microgrid battery bank? Not quite. Yes, Ray, my microgrid battery bank is 40 power plus energy life for 8Ps, SPs, whatever. So about 152 kilowatt hours, whereas my car's only about, I don't know, it's a Model 3 Tesla. I think that's about 50, 60 kilowatt hours. So, yeah, not as much. But remember, my microgrid supplies 7 homes, multiple labs, community buildings, EV charging stations. So it's got a lot more work to do. And we're about to really enlarge it too. So we were most fortuitous that 2 megawatt hours of batteries turned up and 3 250 kilowatt inverters to go with them. So we're building some big stuff here at the Smart Energy Lab now. Oh, thanks, Ray. 56 kilowatt hours. There you go. I don't even think about it really. I just check how many kilometres range I've got, and that's all I care about. So yeah, it's not much of a factor that I consider, but I might do once I start doing bidirectional, which is possible right now with the equipment I have, which is a SIG Energy Site Install 10 kilowatt 3-phase with 32 kilowatt hours of battery and a 25 kilowatt bidirectional DC charger. But I've still got to wait for Tesla to allow it to happen. So we'll see what happens there. Charles mentions, I think Charles is in New Zealand, our government not only removed the purchase incentives, they have now added the road user charge. Yeah, right. Charles, the Victorian government tried to introduce a road user charge. Well, they did, but they got challenged in court and had to pay it all back. In fact, my partner got a cheque for $1,000 for the illegally collected road user charge. And it came down to the fact that in Australia, it's actually a federal responsibility, any enforcement of road user charges, and state governments aren't allowed to do it, and they just overstepped the mark. But yeah, that's a bit of a shame. But again, I guess there's arguments for it, which is if you use a road, you wear it out a bit, and you should pay some contribution to it. And it used to be done through, of course, fuel excise, but with an EV, they don't see it. Yeah, but then again, if you're trying to incentivise a transition to renewables, incentivising EVs in every way you can is a great idea. I mean, take China, for example. I've just come back from there last month. I think, where is it? Shanghai has free registration for EVs. You might think, oh, it's a bit of an incentive. Well, actually, register a normal car in Shanghai is almost the cost of a car. So they basically halve the price of EVs just by taking off the registration costs. So what you now see is like almost every second car in Shanghai is an EV. They have a green number plate too, just to sort of promote it. In fact, China now, I think for new car sales, 38% of new cars are EVs. China's leading the world with the transition. Yeah, that's pretty impressive. Anyway, back to this diagram. So what is the problem? Okay, we've got, we need a means to isolate an inverter. So inverter is generically known as power conditioning equipment, or PCE. So if you see PCE written there, it can mean an inverter, but it can also mean something like a charge controller. Anything that modifies voltage, frequency or current is PCE. But I'm going to be talking about inverters today because it's kind of the most likely scenario. And when you need to be able to isolate an inverter from its energy source, in this case a PV array, so we'll have a PV array connected. It's not drawn here yet. We need to be able to isolate that PV array for both maintenance and safety, and also under fault conditions. So if something goes wrong and you need to remove that inverter, you need to do it safely, not with the fault current passing through it. So we've always required isolation adjacent to the PCE, and these days it can be incorporated into the PCE as well, so you don't have to have an external DC isolator, but you may well choose to have one, or the product that you choose doesn't have an integrated compliant DC isolator built in, so you're going to have to install an external one. So I'm really focusing on that external device that the installer has to select here. So let's check it out. So we've got a 600 volt open circuit array here, so VOC 600 volts. And in this little diagram, I'm just imagining that we're going to have two series switches, and they gang together, hence the little dotted line here. They gang together. And so when I operate this ganged double-poled switch to turn off what I'm effectively in this diagram is a short circuit, I'm going to see up to 300 volts across each switch because they are splitting the voltage equally. So this is explaining how putting switches in series reduces the switching voltage across each switch mechanism, what we often refer to as a pole. So, greetings Wrigley, beautiful Nelson, you're in, sunniest part of New Zealand in terms of sunlight hours. Yeah, great climate. For those who don't know, I'm actually a Kiwi. I grew up in Wellington. I came to Australia when I was about 26. Yeah, I go back to New Zealand very regularly. About half a dozen times a year to run training courses over there for, mostly it's done through Ideal Electrical. They've kind of been really great in organising the venues and facilities. So if you're interested in any of the courses I do face-to-face in New Zealand, contact Dave Petrie from Ideal Electrical. Okay, so that's the problem. Now, I've just drawn it here with an inverter in the middle. So imagine we put an inverter in the middle and we've got a PV array connected to it. So we've still got that same situation. We've got two series switches. Now, that symbol, by the way, with the little circle in the bar means it's load break. That means it can be operated under load. That's pretty important. So technically, these are known as switch disconnectors. We just call them isolators for short. What I've shown here is a galvanically isolated inverter. Now, galvanically isolated means that between the AC side here, active and neutral, and the DC side here, so we've got positive and negative, there's effectively isolation, and that's done by a transformer. So we have inside an isolating transformer, so no electrons from the DC side are capable of leaking to the AC side. Galvanically isolated inverters were the norm up until about 10 to 15 years ago when they all went away. Now, there's nothing illegal about galvanically isolated inverters. In fact, for off-grid applications, they're really very common, and particularly if you've got a battery system that is extra low voltage, you do need galvanic isolation between your battery and your AC or any other source that's LV that feeds that PCE. But let's talk about grid connect systems here. So this galvanic isolation does give some definite safety advantages, but we decided to, well, I shouldn't say we, the industry moved away and moved to transformerless. And transformerless is, and by the way, the symbol for galvanically isolated, which more technically is known as separated inverter, even more technically, simple separation. So simple separation is just some varnish on some windings on a transformer, and you're just relying on inductance to pass the energy. Is this double line. So this double diagonal line here represents simple separation within the product, within the PCE. Okay. Oh my gosh, we've got someone from, I guess it's South Australia, SA, unless it's South Africa. Got to watch SA because I'm actually going to South Africa in February, and everyone refers to it as SA over there. So, yep. So, Sebastian, are you SA as in Africa or SA as in Adelaide or South Australia? Cool. Poor old Wrigley, it's not very sunny today. Well, don't you worry, it'll be back. In fact, it's one of the great things about designing systems for solar is that the sun is incredibly predictable on average. You have good days and bad days, but the seasonal variations are so predictable. There's, typically less than 5% difference between the best year and the worst year in terms of solar radiation. Even though the weather can be completely different, the sun is much more predictable. Yeah, so now what I've shown here is what in common parlance is known as a transformerless inverter. And once again, inverters are a type of PCE. And more technically, a transformerless inverter is a non-separated inverter. So no galvanic separation between the AC side and the DC side. Now, g'day Sebastian, deep South Australia. Right, how deep is that? Cool. Yeah, so when it comes to non-separated inverters, we're relying on some inbuilt safety features such as earth fault detection and earth fault alarms in case of a problem. But this is where this switching arrangement is impacted. Now, you might think that we've still got those two switches there and they're in series, and therefore when we operate them, because they're ganged, the dotted line indicates that they're ganged, that we would be interrupting the voltage, the 600 volts, in two 300 volt sections. So 300 volts here and 300 volts here. That is true under normal operation, but these have got to work under fault conditions, and fault conditions make this all a bit messy. So let me bring a fault condition in. Okay, so now I've drawn an array with a 4-poled DC switch, or it could be a circuit breaker. Of course, the symbol's different for a circuit breaker. It'd have a cross there instead of a circle. But this is a very common arrangement for a DC isolator, is to have multiple poles. And you'll notice that on the positive side, so this is our positive side here, we've got 2 poles in series. So 2 poles in series on the positive side, and we put a little link in here to join them together in series. And then on the negative side, we've also got 2 poles in series. All very good there. And so that's the input to the non-separated inverter. Now, the problem comes when we have a fault. Now, I'll get my red fault pen out here. Not unusual to find that cables are damaged, whether it's by poor installation, whether it's by lack of maintenance, whether it's by one of those lovely Australian possums chewing your cables or something else, and we end up with a short to earth. Now, how do we get that short to earth? It's a requirement to have equal potential bonding of array frames. All conductive parts of a PV array, including the modules frame, must be bonded to earth. So there's a ready path to earth. And you might think, well, it's actually making it easy for a fault to occur. But it actually is helpful when that fault is a relatively weak path, like high resistance. The inverter can detect that fault and shut down. So in a way, it means the inverter can identify that there is an earth leakage to frame or other and shut down. But if that's what's known as a bolted fault, i.e. a really low impedance connection, so the wires have been chewed through and are resting firmly onto the frame or rail, we've got a really good bolted earth. We now have an unfortunate situation with a non-separated inverter, or PCE. When it is operating, it's effectively passing current directly through, like this. Positive through to the AC side, negative through to the AC side. And of course, these switch like 100 times a second to create AC. But at any one moment, this is true, that for instance, at this moment, the negative is connected to the neutral, and there is no transformer to isolate. So we now have a path. If we follow this fault, it's going to go down across here, and it's going to look for a path back to earth, and it's going to go, it's going right through my system and back up here and back to here. So we now have a fault through the system, not only through the PV array, it's going through the inverter, it's going through the MEN. So for those who are not familiar with Australian and New Zealand standards, we're technically known as a TNCS earthing system, which means we bond the neutral conductor at the main switchboard to earth, and we call that a main earth neutral, or MEN. So under this situation, this fault, I need to remove the inverter because it's dead. It's fully dead. Once this fault occurs, and most inverters cannot sustain a direct bolted fault on the DC side. In fact, inverters are required to meet a test under IEC 62109 parts 1 or 2. I can't remember which one it is. And it's 300 milliamps of leakage to earth. Not 9 amps or whatever the array can put out. So it's a very small amount of leakage the inverter must be able to interrupt and shut down safely. But if you get a hard bolted earth fault, it generally takes out the inverter. And they fail in pass-through. It's only semiconductors in there. They just burn out. So you end up with a melted bit of electronics that's just conducting DC through to the AC side. So we need to take this inverter off the wall and replace it. But that means we need to be able to isolate it. So we go to operate this switch here, and you'll notice that even though it's got 4 poles, only, in this case, only 2 of them on the negative leg are going to interrupt the current. So we've now effectively moved this 600 volt open circuit problem across just half of the DC isolator. So those 2 poles have to break 600 volts. Not like in our earlier example with a galvanically isolated inverter, we're separating it to the positive side and the negative side, 300 volts each. Now with a non-galvanically isolated inverter, we've got to switch it on just one side. So now I've explained the problem. Let's look at the solution. And I'm going to take you into Australian standards for this. Now, I say it every time because it's such a good deal, but hang on, I'll bring myself back up here. It's such a good deal that the Smart Energy Council have a program called the Smart Installer Program. It's free to join. Anyone can join. And as part of that, you get access to 15 joint standards from Australia and New Zealand. The PV array standard, the battery standard, the inverter standard, the standalone power system standard, and some ancillary standards as well. So it's a great deal. It's worth thousands of dollars. I think around about $5,000 in Australia. Probably a fraction of that in New Zealand because you guys don't have a ridiculous pricing we have here in Australia for standards. So there you go. You should sign up for the Smart Energy Council Smart Installer Program. If I remember, I'll put a link in the description later on, but you can just Google it. Smart Installer Program, Smart Energy Council. I guess the only thing you're giving away is your email address and name. So if you don't mind a little bit of industry spam, that's a small price to pay for having access to the standards. So I'm actually going to bring up a copy of the standard now. Now let's have a look. And I've got to bring up the computer. And here we go. So this is from one of the appendices in 5033, the 2021 edition. Now, apologies to Kiwis. I know, hang on, I've got to do a proper apology. Apologies to Kiwis. You haven't yet had the latest version of our joint standards ratified in the New Zealand electricity regs, but we're under good advice from your government, from New Zealand government, that it's going to be gazetted probably in April. And that will mean that you'll come in line with Australia with your PV array standard, your inverter standard, and the new battery standard will all be covered under New Zealand electricity regs. So woohoo. As someone who trains a lot in New Zealand, it's such a kind of don't ask, don't tell kind of scenario because the lack of compliance with with old versions of the standard when new ones are around that allow you to do more exciting and safe things. So there you go. So back to that standard 5033. So this is from Appendix C of 5033 2021. And it's really just showing a fault condition as I've just drawn. Now, given that it is kind of getting to the silly season, I'm already into the apple juice. So just to wet my whistle a little bit. Right, so let's go through how we voltage rate that switch. And look, I really should emphasize that this standard is very useful. Like the appendices provide you with worked examples, and we're going to go through one of those worked examples right now. And, if you're someone who's in the industry and has to read and comply with standards, often you only look at the body of the standard and don't worry about the appendices. The appendices are there to inform you. Some of them are not just informative, but also normative. That means to comply, such as the lightning requirements. Have a good fish around down deep into this standard when you're relaxing on a beach somewhere. So let's have a look at a worked example here. And this is examples of calculating, example of calculations for determining suitable voltage and thermal current. Now, what on earth is thermal current? What it means is that the rating of switchgear is actually derated with temperature. So as it gets warmer, the ability to interrupt fault or any currents diminishes. And in this standard, we actually have two kind of temperature set points that you need to consider. We've got a 40-degree thermal rating and a 60-degree thermal rating. The 40-degree is for indoors or at ambient temperature, or outdoors at ambient temperature in full shade. And the 60-degree is if you're exposed to solar effects, i.e. the sun shines on your enclosure, on your switchgear. So that means that the thermal ratings drop. Now, these are all covered in the test standard for, in the case of DC switch disconnectors, an Australian adoption of the IEC standard 60947.3, if you're really into numbers. And there it is, AS 60947.3. And if you're using circuit breakers, it's .2. So .2 is for circuit breakers. Now, the requirements of 60947.3 lists all those ratings that need to be tested. So a manufacturer needs to be able to state what these things are for their product. Now, there's a few things I'll just explain. U is for voltage. Maybe because it's in some language, voltage starts with a U, I don't really know. So the rated operating voltage. I, as in for current, and I think I is used because of intensity. I don't know why we use I, but we do. So I is for current rating, so IE. And then we've got these interesting ones under Part C. Now, this is kind of the important ones. These were adopted by an amendment to 5033 in 2014, Amendment 2. So it comes from quite a way back, that we realised that switchgear can have a continuous rating, which is relatively low, let's say 20 amps, but it can momentarily interrupt or make, so that's the make or break, a much higher current a few times. So that's known as a the ability to under fault conditions operate. So we've got, it's known as a utilisation category. I just forgot the term for a minute then. And so we require a utilisation category of DC 21B, which is at least once every 30 seconds. Now, what's a bit scary is I've looked up some products to see what the utilisation category was and what the number of operations. They only tested them for 5 operations. So to pass this test, I make and I break, you only have to do it 5 times. So I guess what it's saying is that a DC switch disconnect is really an emergency switch or a maintenance switch. It's not something that you would do every day. You don't turn it on and off every day because you'll soon get over that probably very low bar in terms of its ability to continue to operate. And if anyone's ever done this in a slightly dim room, you can actually see the arc inside the enclosure sometimes. It sort of makes a lovely sound as it interrupts the arc, and there's a little bit of a glow inside the enclosure. It's doing some hard work. So that's I make, I break. And those values are always a lot higher than IE, the operating current. And then we've got ITH, thermal, for thermal ratings. And there are thermal ratings for 40 degrees and 60 degrees, and both of those under what's known as IP54NW. Now, this is a strange one. You might think ingress protection is kind of just basically 2 numbers, and then it's got some letters after it. NW stands for no water, and it's a bit of an Australian, New Zealand invention. We've added that. So what that means is that if your enclosure has any wires terminating within it, you need to have a means to allow any water to leave, i.e. a drain. That's right. So DC isolators require a drain if they have terminations inside them, which of course they do. So that's the no water bit. Isn't this getting exciting? So let's go down a little bit here and look at those temperature ratings here. I'm just checking the chat here. Everyone's very stunned and quiet, so either you're finding this all a bit dull or you're just trying to take it all in. So I'm going a bit slow. So here's those temperature ratings for iThermal, ITHE. And you notice that there's 40 degrees for indoors, 40 degrees for outdoors without exposure to solar effects. So if you've got an inverter with a DC isolator on the wall, but it's not exposed to sunlight, then it's also a 40 degree rating is required, a minimum 40 degree rating for your ITH. But if it is exposed to the sun, so whether it's on a roof or on a wall, then you need the 60 degree rating and that wonderful IP56 no water. So here's a worked example. And so we're taking an imaginary DC switch disconnector, and it's got a rating for 40 degrees in the shade here of 32 amps. And it's got a thermal rating indoors, but it's enclosed and the rating drops. So there's a big difference between unenclosed and enclosed. So this particular one, ITH without the E, is unenclosed, and then with the E on the end, it's enclosed. Therefore, it's going to get warmer. So the rating drops to 25. Outdoors in shade and not subject to solar effects, it's also 25 amp rating. But the worst case scenario, which is the one we'll follow, is basically exposed to solar effects and its rating drops down to 19 amps. So look at that. Something that you might look at the box and it says 32 amps, but when you stick it on the wall and exposed to the sun, it's only 19 amps. So, 30% reduction in current rating. So we come down to different configurations. Now, this is where people get confused. They will take a device. Let's bring in a circuit breaker just for fun. See if I get my little overhead working here. Where are we? Overhead. Here we go. So this is a DC circuit breaker from Noark, a pretty popular brand. And it's got 1, 2, 3, 4 switched poles. And they gang together like this. So off and on. By the way, we in the standard refer to not off and on, but in the open or closed position. So that's a closed position. That's an open position. The contacts are apart. So how many poles have I got? Well, I've got 4, which means I can use this product to create this arrangement here. So I could actually wire it up like this. And I'd need to put some little links in, so some little links like this to create. Where are we? To create that number of poles in series on each side, the positive and negative. So there we got some little links popped in there. And that's effectively the same thing. So I've got 4 poles, but remember, with a transformerless inverter, it's not going to go through 4 poles, only going to go through 2 in series. So even though it's a 4-pole device, I need to know what its 2-pole in series rating is. So that's where we come back to this table here for this imaginary DC isolator. And it's showing us ratings for 1 pole, 2 poles in series, and 4 poles in series. You might go, well, 4 poles in series. Well, that could be for a galvanically isolated inverter where it's always going to switch all 4 poles. The current is always passing through all 4 poles. Or it might just be a big mother like this one. There's an 8-pole DC isolator. And, on one side, so that's the negative side, 4 poles in series, and the opposite side, another 4 poles in series. So that would also be 4 poles switched under earth fault with a transformerless inverter. Oh, since I've got this here, by the way, I want to show you something that has caught a few people out. And it's potentially quite dangerous. Maybe I'll show you in a very practical way. I'll just turn my meter on and use my ohm meter to menu, beeper, menu, beeper. See if it's going to work. Here we go. Beep, beep, beep. You can hear that? Good. Okay, so you might imagine, let me just compare it to that circuit breaker. Let's turn the circuit breaker on, and this DC isolator is on. I'm going to see what happens when this is on. Okay, top to bottom, we have continuity, right? I can turn it off. Turns it off, right? Good. What about other poles? Nothing, 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 right? So it's only switching that. But with these tiered type isolators, it's quite confusing. If I make sure it's on, yes, and nothing, nothing, nothing. Oh, look at that. So it's from top left to bottom right is the switch. So that can really catch you out because you can accidentally wire it in a dangerous way if you think it's a pass-through. So it's good to do a continuity test. And I actually took out the links. This normally has pre-installed some little links like this to create a 4-pole and series arrangement on this unit. So there we go. I took them out just to show you that wiring arrangement within the product. So there, a little practical demonstration. Okay, where was I? Let's come back to this table. And I'm just checking the chat here. Oh, g'day, Frank. Frank, you still in Africa at the moment? Good to hear from you. And Wrigley says, I noticed some commercial installs that have the inverter enclosed in a stainless steel enclosure. Does this change the rating as it's not strictly directly exposed to sunlight? If the inverter has an inbuilt DC isolator and it's tested to 4777 Part 2, it would need to meet those eye thermal ratings. But if you're installing one yourself as an external DC isolator, you'd need to ensure that if it's indoors and enclosed, there is a rating. And if it's outdoors, even if it's enclosed, that's still, if it's exposed to sunlight, considered solar affected because the sun's going to heat up that enclosure. Ray asks, I notice the level on both ends is how you would note the connections as well by now, high or low as they are. Yeah. So I think Ray's identified that because these are tiered, the switching is horizontally across. So the bottom one is the bottom here, is the bottom one on the input side or other side. So yeah, the switches are arranged that way, horizontally. Yeah. Incidentally, I got these because they were put on a large megawatt scale commercial system, and the inspector noted that they weren't correctly voltage rated for open circuit. So they had to take off. I think I got about 50 of these from a job, and they've never been used. So they've been quite handy for some of my projects. Yes. So coming back to 5033. In this example, we're going to look at 2 poles in series, so a 4-pole DC switch with only 2 poles are switching when there's a fault condition. And there's our voltage and current ratings for open circuit voltage, our operating current, and our I make, I break current. Look how big the difference is between operating current and I make, I break. It's huge. Oh, Frank, welcome back to Australia. Frank's been doing some amazing work in Africa. Good on you. Okay, so let's go on with this worked example. And there's, I think, 3 worked examples in this standard. So I'm using this examples from the standard because you can then go and follow with a copy yourself to refresh your memory without having to watch my whole video again. And I think it's a really useful thing in this standard to have, because if you read the body of the text, it's really a bit confusing, and the worked example makes it all very clear. Okay, so in this arrangement, we are selecting a switch disconnector with a separated inverter, so emphasis on separated, i.e. galvanically separated, i.e. you probably can't even buy one anymore. So this is kind of old school now. And in this example, the PV array is connected to the inverter. The maximum voltage under temperature compensated conditions is 1,000 volts. There are no DCUs. Now, why does this matter, DCUs or DC conditioning units? I actually covered this in a previous Toolbox Tech Talk last week somewhat. DCUs or DC conditioning units, often referred to as optimizers by the marketing people, are a device that sits between a panel and the string to which the panels connect. And it means that the output voltage and current is controlled by the DCU, not by the panel. And so there are more different calculations. So effectively, the DCU determines the maximum current from the module, not the module itself. So to keep it simple, we're saying there's no DCUs. Incidentally, DCUs are a very small part of the market, from my understanding, probably only about 1%, I'm guessing, less. Warwick Johnson from Sunwiz knows otherwise because he's the data guru in Australia. But yeah, I'd say it's a very small percentage anyway. So that's why we're focusing on this example with no DCUs. It's a single string. That means the panels are connected in series, but there are no parallel strings connected. The short circuit rating of the module is 15 amps, known as ISC mod, and that'll be written on the data sheet. It'll be actually a mandatory on the back of the panel on the compliance label. And the K factor, the bifaciality factor. Now, I did cover this last week, so if you're wondering what on earth is K, it's not special K, it's just K, I, and it's the amount of extra input from the back surface of a panel. Now, bifacial panels generate current on both the front and the back, whereas a conventional, when I call it conventional, because it used to be the most common type, monofacial only generates current from the front face. So in this case, we're just using monofacial, and therefore bifaciality is 1, meaning there is none. So we don't have to increase our current rating from our modules to allow for bifacialness. The switch, this connector is installed outdoors and exposed to solar effects. So it's on a wall or on a roof, and it's going to be getting hot in the sun. So it's going to have that eye thermal of 60 degrees. So let's go down to the solution. And the solution here is, first we've got to find out what the calculated current of the PV DC circuit. Now, it's important to understand DC circuit includes all components that contribute to that circuit. So in this case, it's only the module or the modules, the PV array. We don't have any DC battery connected directly onto the array cable, but we do require a 25% safety margin. So this 1.25 times is additional to allow for a bunch of things. So modules have a certain amount of variation in their manufacture. So you'll see that their ratings will be typically 0 to plus 5%. So you might end up with all your modules are 5% higher rated. So that's going to mean that you have more current. But the big one is irradiance. Now, panels are tested, and that's what the ISC module is, at 1,000 watts per square metre. In Australia and New Zealand, because we're in the southern hemisphere, and woohoo if you live in Africa as well, you've got very clear skies. And certainly when the clouds aren't there, there's not a lot of particulates that reduce the irradiance. So we get more than 1,000 watts per square metre on a clear day, particularly in spring, I find. I've seen 1,200 watts per square metre. So that means irradiance is proportional, current from a PV array is proportional to irradiance. So you're going to get a lot more oomph, a lot more current coming out of your panels at higher irradiance. So that's what the 1.25 times safety factor. And it's nothing new, actually. It's been around ever since the 2012 edition of 5033, because it referred to the DC circuit, and people sort of seem to ignore that for quite a while until it was really hammered home in the latest update. So we multiply those through and we find that our 15 amp ISC is, with a 25% safety margin, is going to have a short circuit current of 18.5 amps. Okay, so that's what we've got to be able to interrupt safely with an I make, I break setting. So we use the table 4.2 to find the thermal current rating. And let's have a look. We'll go down here. And because this is a separated inverter, there is no positive circuit configuration or negative circuit configuration that needs to be considered, because they're combined. That means they're breaking both the positive and negative at the same time. And so the voltage rating is 1000. As long as our continuous operating current is greater than 18.75 amps, we're all good. Okay, and let's go down here and have a look. And have I gone too far? I've gone too far, sorry. Whoops. Okay, so it looks like we're fine, because hang on, I've got confused here. Got to go right back up to the table for our sample switch. Our switch is rated for 19 amps, and with thermal effects, solar effects, sorry. So the iThermal is 19 amps rating, and it turns out that our switch gear, sorry for making you jump all over the place, is going to have to interrupt only 18.75. So we just squeak in. We squeak in under that 19 amp rating for that switch gear. But that's only with a transformerless inverter. So just ignore all of that, because it's not applicable anymore. So I've just shown you something that you probably won't have to consider. Now let's look for a non-separated inverter. So here we go. Selecting a switch disconnector to use with a non-separated inverter, and we've got here a 500 volt open circuit. So it's not as high as previously, so it's only 500 volts open circuit, and there are no DCUs, as we explained before, and the PV array has only one string. So the ISC of a module is also the ISC of the string, but we've got to apply the K factor, which is 1 because they're not bifacial, and the 1.25 times safety margin. So we come down here, and because this is only a 9 amp ISC, these panels have a lower current than the previous example. We have 11.25 amps of potential fault current, allowing for high radiance, and now we have to find a switch that can interrupt 11.25 amps, but now it's on only the positive leg or the negative leg, so 2 poles in series in this example, not 4 poles in series. So we go down here and we see that on the positive leg we could have up to 500 volts with an earth fault, and on the negative leg up to 500 volts with an earth fault, and the combined really doesn't apply under an earth fault anyway, because we're going to have it passing through the inverter through to the MEN, so it's not actually passing through both poles. So we go down to here and find out that that looking up on the table, we've got a 32 amp rating at 500 volts for 2 poles and for 4 poles in series. So 2 poles would be what we're concerned about, and it's way more than the 11.25. So this switch can be used with either 2 poles or 4 poles in series. So either way, it's just fine. Okay, last example. And that's a diagram of that configuration, by the way. The last example is, once again, another transformerless inverter. And this one is a little bit different. We've got 2 parallel strings. So everything else is similar to the previous example, except instead of 1 string, we've got 2. And we've got the same 9 amp modules, so 9 amps. So we're just trying to pump in more current into that same MPPT of the inverter. So we run through the equations now. There's that same equation before, 1.25 times K, K being bifaciality is 1 because it's not bifacial, but we've now got two strings. So that 9 amps is times 2, which means we're up to 22.5 amps of potential fault current. And using the table H2, we find the thermal current rating for the location, in this case, is only 19 amps, remember? If I go back up, I won't do it now, back to table 4.2, you'll see it's only 19 amps. So therefore, this switch does not meet the current carrying capability at the operating ambient temperature. So this switch cannot be used. So there you go. It's all dependent on topology. Topology is the way we describe the way that an inverter converts DC to AC. So topology is either transformer-based or transformerless. If you're a geek, you call it separated or non-separated. There you go. Now, just checking for any questions here. Yep, Ray points out that KI was covered in last week's episode. So you can always just go back to my YouTube channel, Smart Energy Lab, and you'll see all the Toolbox Tech Talks that I've been doing. So that's kind of fun. Well, we've got just a few minutes left. I wonder if anyone's got any questions. I'll throw them into the chat. Oh, actually, there is one more thing I wanted to cover. And I'll maybe bring my overhead back in. Where are we? Okay, so here's a real DC isolator. Actually, it focuses a bit off. Let me see, sharpen the focus for you. There we go. So, popular brand in Australia, certainly, said Benny. Oh, sorry for the wobble. Overhead camera, stop wobbling. There we go. And it meets a bunch of requirements. So, actually, this is the older one. And I don't think, normally it has IP66NW written on there, the newer versions, because we introduced the no water requirement. But a bunch of things. You've got to have marked on and off on the unit. So markings are actually a mandatory requirement. And on the side here, they very helpfully, if I can make this a bit bigger, see if I can make it a bit bigger and zoom in for you. There we go. Very helpfully on the side, they show some different configurations and voltage ratings. But the thing I want to point out is that little symbol, see if I can do this with one hand and point with the other here. This is known as an RCM marking, Regulatory Compliance Mark, RCM. And it basically means, and it's an Australian New Zealand Regulatory Compliance Mark, and it means it's actually been approved as a product for what it's deemed to achieve. So it's kind of like a guarantee that this is not just fluff. So this switch has met, for instance, IEC 60947.3. In fact, I think they even list that on the bottom here somewhere. And look, they also list the utilization category. There's DC21B, which in the latest version of the standard is now called DCPV2, which is the operate at least once every 30 seconds. So there's quite a bit of useful information just written on the side there. They even list compliance to the old 2014 standard. So this is an old DC isolator I've had on the shelf for a while. They've probably updated this to show it's compliant to the 2021 edition for iMake, iBreak, and iThermal. So there you go. So, RCM, it's a thing. In fact, a bit more than a thing. See if I can bring up the RCM page for you. Where are we? Regulatory marks. There they are. And computer. So that's from the weess.gov.au website, which is the entity that covers, I think, both Australia and New Zealand for compliance of electrical safety of equipment. And so it's a level 3 product, a switch disconnector, and it's a requirement to have that RCM mark. It's not just a feel-good thing. So there you go. That's what that little tick's all about. Cool. All right. Well, it seems that we've not got any more questions coming in here, so I think I'll probably wrap for today. So once again, thanks everyone for watching yet another Toolbox Tech Talk, and I'll be back in another week. Okay. See ya.
I don't need to analyze every word that comes out is a lie. Make it look like you're so ice. You won't make it to the finish line. Now if you gotta know the truth was gonna let you go. You was fine, never mind, unpredictable. Feet eye off the ground, you ain't no one. You a star, blow it up like supernova. In the nighttime, hit my hotline. Sharing secrets, you wish really was part your life. Basic bullets, with no bullets. Does your wifey know you're begging for my notice? Promise you're the same, running for the meds. Show you like my vibe, that's my candy on my wrist. Bad habits,